DDS is, I use this for an example. It is a publish-subscribe technology, and probably most of you know what this means, but it's you have entities that need to publish data, they have data that need to be published, you have entities that need to subscribe to that data and receive it, but they are loosely coupled. So your publisher doesn't necessarily need to know how many subscribers or where they're located. Your application just publishes data, and your subscriber application gets it as it's available. Because it is a standardized technology, it supports interoperable communications. There are open source and commercial implementations available. They all communicate. And it is interoperable across all different programming languages, different operating systems, and hardware platforms. DDS is used not just in aerospace or in DoD applications, but also a lot of different commercial applications, and that just kind of gives you an idea of where it's used. Distributed applications are everywhere, and DDS is a technology that's quite useful for many of those projects. And so why is it useful? Well, there's a couple of reasons. It makes your systems more flexible. It makes it easy to move between different platforms. It's easy to extend your system, to add new components. All of these tasks are much easier when you're using a middleware component, and especially one that has some of the features of the data distribution service. And we talked a little bit about how it just makes your application not as tied to an operating system. It makes it smaller because you can focus on those functional requirements and much easier to port it. I got my timer here. Let me take a peek and see how I'm doing so I can adjust as I need to. All right, so let's get back to system resources and look at some examples here. So this slide looks a little bit about memory as one of the resources. And memory is used by a lot of different aspects here. We've got, of course, our static memory, right? We've got our application, we've got our library size, we've got all of those things that are going to take up memory. And then we have our runtime memory, we have our stack and our heap that we need to understand and make sure we manage. So with DDS, we have the library. And what I didn't mention before is data types. We're talking about communicating data. One of the aspects of DDS is that if you as a system developer define data types that you want to use to communicate, you can define those in a language-independent format like IDL, and then you generate the specific code that's required then to marshal that data onto the wire and marshal it out. So your application is dealing with language, natural data types, is dealing with structures and classes, and that sort of thing. So part of the code is the generated code, DDS generated code. The DDS library is the application code that all goes into your applications. In some cases, there might be a DDS service, although that's certainly not required by the DDS standard. That's all part of your executable code that uses memory. The other parts that you have is part of your transport. If you're using a TCP or a UDP IP-based transport, chances are you have buffers that will hold the data as it's put onto the wire or as it's come off the wire. You have locally created entities. You have, for the DDS architecture, you will create a domain participant to participate on the DDS network. You'll create your data reader or your data writer, and these things will allocate memory as they're created. You'll have discovery, which is the idea for DDS that you create these entities for communication, and you don't need to, as a publisher of data, you don't need to know where your subscribers' data are. DDS can manage this, discover them automatically on the network, and do the connections, and that requires a little bit of bookkeeping. And then there's the history caches. When you're writing data and when you're reading data, you can keep a copy of what's written. One example is if you want to do reliable, your writer, your application will write data, and that will sit with the writer. And then the writer will hang on to that until it has positive acknowledgement that all of the connected receivers of data have received it. And so there's this idea of a buffer or a cache at the writer side, and then again on the All right, so that was a little bit long-winded, but it's an example of the different parts of DDS that can consume memory. And then we go into resources for CPU, and what we look at for CPU is threading policies, for example. Depending on if you have a multi-core CPU or if more typical in embedded systems, if you have just a single core CPU. How many threads do you want? Is that going to save you time, be able to distribute across multiple cores? Or is it really just going to take up extra time for context, which is when you only have one core to run on, and maybe you're better off with just a single threaded application. And then we also consider event notification. So is it a busy waiting? Is it a polling? Is it an asynchronous notification? How is the application notified of events that happen within the middleware? When we're talking about communication, that is like, for example, data is available, or maybe there's a new subscriber available on the network, all these sorts of things. And then the other one we look at when we're talking about communication middleware is the network. Obviously, that's another resource. And the things like the data encoding, how is data encoded to go out into the wire? What kind of overhead is there? Is it possible to aggregate or batch our data before putting it onto the wire? And then what kind of protocols are there for discovery or for reliability, for handshaking, liveliness, these sorts of things. Okay, so now we're going to switch gears just a little bit and talk about, now that we've kind of gone through the background of DDS, talk about managing these system resources. So how do you do this with DDS? I think we've talked about a lot of these things. I think we all know this, and it's just kind of an interesting note out there. As an architect or a system designer of these systems, your decisions are always a balance, right? There's a balance between the performance and maybe the amount of memory you're going to use for your application. There's a balance between how flexible your application is versus how much code you had to write to give you that flexibility, right? So there's always this balance and this trade-off. And as you're looking at resource utilization, certainly that's always a balance in the decision-making process. Okay, so one of the things that impacts resources used is just how you use this middleware component. And that's what the next couple of slides talk about, are some examples of how you configure and how you use this middleware. And you can make design decisions about it that really affect one way or the other, how much memory you're using, or maybe how the CPU is used, how the network is used. So this example talks a little bit about architecture. DDS has this publish-subscribe architecture. You define the data types that are used, and you define the topics that you're going to use for communication. So this example talks about, it's just a simple application that publishes shapes, different shapes of different colors. So maybe your data type is very generic. You have just one data type that's a shape, and as part of your field is what kind of shape it is, and another field is what kind of color it is. Well, now you just have one topic, and all you need is one data writer and maybe one data reader to write whatever kind of shape you want to write and read whatever kind of shape you want to read. And another option, certainly another way to architect this, is to do multiple topics. So maybe you have a writer that knows how to write squares, and a different writer that knows how to write circles, and a different writer that knows how to write triangles. So in order to put together your application that's required to write these three shapes, on one case, you have fewer data readers and data writers to get the same idea across, and over here you have more data readers and data writers to get that idea across. Well, this is going to affect how much memory is used, first for creating these local entities. I have to create more entities, I have to use more memory to do it. And then also for discovery on the wire, because I have to keep bookkeeping about all of my matched peers out on the network. And if I have more peers that I have to keep track of, then I have a little bit more bookkeeping involved there. So just one example of how design decisions can impact how much, in this case, memory is being used. All right, let's see. I'm going to go through just one more example here quickly. So this talks about defining your data types. And And so looking at that same example, maybe we decide that our color is just a string. And so now we have to decide, is it an unbounded string, because I could have red, which is very short, or I could have purple, which is a little bit longer, or I could have, I don't know, a very long sort of color name. Or do I bound that and make it a bounded string? You think maybe this is not a big deal in design, but it can be a big deal if we're talking about writing a lot of these data samples. Well, this over here is quite nice because it's bounded, and it means what we can do, we can make some decisions. We know exactly how much memory we're going to be using. But once we multiply this out, we're using quite a bit of memory to allocate the samples or the data that we're going to be reading or writing. Whereas over here, if all we have to allocate is what we actually use, then a lot of times, well, we can't pre-allocate it ahead of time. We have to kind of do it as we're running. But we tend to save space because we're never allocating more than we need. And so we look at here in this example where we have, I forget how many we have. I guess we have 100 samples going on here. Then it can make quite a bit of difference as far as how much runtime memory is being used just to hold 100 copies or 100 instances of these samples. All right, so this is kind of obvious. Early insight allows for better system planning. It's also kind of the challenge too, right? In order to do this, you need to have the tools available to be able to plan, to be able to estimate, right? You're going to put the system together, and I need to be able to estimate if I have this architecture with these kinds of publishers and these kinds of data, how much memory should I expect that to take up, and how much processing, how much CPU can I expect that to take up. So you need the tools in order to be able to plan, and then you need the tools to be able to measure as you're running and as you're implementing to see if you're staying within your expected design and to be able to make changes if necessary. So there's basically two ways to do this. Assuming that you're getting a middleware component that's a commercial component, you don't have access to the source code, so all you have are the specs on it. You can measure the utilization from the outside, and this is using operating system type tools, right? You're doing a PS, you're doing a top, you're looking at the kind of from the outside of the process, how much memory, how much CPU is being used. And then you have measuring from the inside, which is obviously going to give you a finer grain of detail and more information as you're executing and as you're running as to what's being utilized. And this is an example from DDS, and I think this is again it's looking at memory, where in this case this DDS product has you can run it and turn on instrumenting of memory operations. So what gets logged then and recorded is every memory allocation and deallocation with a tag of when it happened, a timestamp, and where it happened. It was in this data reader, or it was in this topic, or it was in this data writer, which really gives you the ability to look in and go, wow, my publisher, this publisher over here, this writer of data is taking up a great percentage of my memory, and why is that, and can I do some reconfiguration or maybe a little bit different design to change what's going on. And that's much harder to do if all you have are the outside tools. I'm getting close to time. All you have are the outside tools for the operating system to look at what a whole process is doing. It just gives you better tools.